Hello everyone, welcome to my presentation or video on Quasilinear time decoding algorithm for topological codes with high error threshold. My name is Mark and I've been working on this project the past year as part of my master thesis together with my supervisor David Elkouss. We're located at the QTech Research Institute at the Delft University of Technology in the Netherlands. So let's get it started. In this presentation, we'll be first covering the basics of surface codes. We'll cover two decoders for the surface codes. After that, we'll move on to the matching Way heuristic, which hopefully will give motivation to the development of the unified balance film decoder. So, surface codes. We'll be giving an introduction. We'll introduce the noise models that we'll be using in this presentation, and I'll give an introduction on decoders. So I think most of you are very familiar with the surface code. It's a family of error correcting codes located on a 2D lattice of qubits. Here the data qubits are located on the white circles. And on the vertices and faces of the lattice, there are ancillary qubits located which are used for parity measurements. In this case, on the vertices there are star operators which are equal to X parity checks, and on the faces there are plaquettes which are equal to Z parity checks. Now the surface code that you're looking at here, that is a toric code. It's a torus. So we have periodic boundary conditions, where in this qubit, the grayed out one is exactly the same qubit as this one, and this qubit is the same qubit as that one. So periodic boundary conditions. Now the error model that we'll be using in this presentation is the independent noise model, or independent parity noise. It's very simple. Each data qubit is subjected to random parity X or random parity Z error. So in this case, in the case of a parity Z error, that will trigger true non-trivial X parity checks on the star operators, whereas an X error will trigger true non-trivial Z parity checks on the neighboring plaquette operators. Now, whenever there is a string of errors, the parity checks in the middle of the strings will cancel themselves out, and they will move, and the non-trivial measurements, they will move to the endpoints of these strings of errors. Now, what does it mean to correct an error? Suppose that we have an error as pictured on the top left, that is right over here. Now, we don't exactly know on which data qubits an error has occurred. The only thing that we know are these measurements. So as per our view, the error could have been either one of these four cases or classes. Now, if we supply a correction operator, which is just a string of or a combination of parity operators, and the class doesn't match the error, what we will end up with is a string of errors that crosses the entire boundary of the torus. And a string of errors that crosses the boundary is equal to a logical operator. So if we supply a correction operator that is from a different class than the error, what we will end up with is a logical error. And it is something that we don't want. Now, to decide exactly what kind of correction operator we want to apply to correct our error, that is the task of the decoder. Now, there are two numbers that we use to compare different types of decoders. The first of which is the code threshold. Now, imagine for a given number of error rate, there is an output decoding success rate. And you can imagine that if the error rate goes up, the decoding success rate goes down. The threshold error rate is the error rate at which point, below which we can increase our input lattice, input surface code, so we can have a bigger toric code or bigger any type of code, and we'll end up with a higher decoding success rate. Now that is something really nice to have. And the second thing that we use is the decode complexity, which is just how the decoder scales in terms of running time with ever increasing lattice sizes. Now, what you would want is a decoder with a high decoder threshold and a low complexity. And the first decoder that we'll be covering here is the minimum wave perfect matching decoder. Now let's call the set of non-trivial parity measurements the syndrome of the lattice. So these are the circles depicted here. Recall that a string of errors, which is depicted by these strings, they trigger non-trivial parity measurements at the endpoint of the strings. Now, a simplified view of decoding is just to make pairings or matchings between these syndrome nodes. In this case, we will have a correct matching because we don't end up with a string of errors that crosses the entire lattice, where the corrections are these dashed lines. And here we have a faulty matching, or a matching that leads to a logical error, because what we end up with is a string of errors that crosses the lattice. Now, what minimum weight perfect matching does is assuming that it is more likely to have a fewer amount of errors than a larger amount of errors. So imagine having a lattice with this syndrome. Again, what minimum weight perfect matching does is constructing a fully connected graph with weights between them, and these weights are equal to the distance between these nodes, and find the minimal weight subset of edges in that graph. So what you end up with is a minimal number of errors, basically, and that is the correction that you apply. Now, in general, this is a good approximation, as the lowest weight error configurations is generally the correct class of correction operator. However, because you would have to construct this fully connected graph and you have to find the minimal weight subset of edges, that it's quite a heavy task. And the minimum weight perfect matching decoder has a bad worst case time complexity, as you see here. It's n cube, O(n) cube. So we tested it with with our own application. We simulated the performance of a minimum weight perfect matching decoder on toric lattice with one only independent Pauli noise from lattices 8 to 64 and a combination of independent Pauli noise with measurement errors, in which case you have to decode on a 3D lattice. And we find these code thresholds, which is very close to what has been reported in the literature. So what we have found is these green values, and what the values that have been reported in literature are these black values. So next, let's move on to the union-find decoder. Now first, we'll be looking at a different kind of representation of the lattice, the graph representation, which will help us understand the mechanics of the peeling decoder and its derivative, the union-find decoder. We'll be looking at its data structure and again the performance of the decoder. So what is the graph representation? On the left, we have our very familiar toric code with the white circles as the qubits. Now within the graph representation, the vertices are what they are, they're the vertices, and the edges are equivalent to the qubits. Note that we have here accentuated the syndrome or the non-trivial vertices or parity checks. Now with independent Pauli noise, we can actually split the graph into a primary and secondary graph, in which and we're looking at the primary graph right here. And in the primary graph, the vertices or the x parity checks are the only vertices in the graph, and in the secondary graph we have our faces or z parity checks as the vertices of the secondary graph. We'll be only looking at the primary graph here, but the decoding of the secondary graph is exactly the same. Note that this is only the case for independent Pauli noise and not the case for the polarizing noise, for example. So what is the peeling decoder? It actually decodes for a different kind of error, erasure noise. Now, erasure noise is when a qubit is erased from the system, but we can actually detect that it is gone, and we can replace it with a qubit of totally mixed state. So basically, it is just a Pauli error with the additional information that we know it has happened. Now, on the surface, a subset of erased qubits can be represented by a subset of edges in our graph representation. And erasure is a connected graph of these edges and vertices. Now, what the peeling decoder does is to first construct connected acyclic subset of edges, which is called the forest of an erasure, and then it moves on to so they call it peel the branches until what you end up with is a matching between these syndrome vertices within the subset of the forest of the erasure. Now let's call the parity of an erasure the number of these syndrome vertices contained within the subset of the erasure. And what you can already see, of course, is that the peeling decoder is applicable for any erasure which has even parity, of course, because you would have to make a matching between these syndrome vertices. If you have an odd parity, you would end up with one that's being left out. But when can these so it cannot decode for odd parity clusters, which is the case when you have parity errors. Now, in the context of the union find decoder or the graph representation, you can view each syndrome, each single point in a single vertex in the graph. You can view it as an odd parity cluster. And what the union find decoder does is to grow these clusters in size until they are merged with another odd parity cluster, at which point you have an even parity erasure, and you can apply the peeling decoder just as before. So we have a visual to demonstrate this. So these two clusters, they keep growing because they are still of odd parity, and now they have merged to a cluster of even parity. And from here, we can apply the peeling decoder just as before to end up with a matching between these syndrome vertices contained with the grown erasure. Now, the union find decoder is it is not originally named so, but it has been given that name by the community because it utilizes the union find data structure. Now, the union find data structure is a directed tree, basically, in which each vertex points to some parent, and the root of the tree is some representative element for the tree. Now, why is it necessary? Because when growing clusters, you would have to merge separate trees, and for trees to merge, you would have to know whether they belong to different trees, and that is what this tree unified data structure is all about. Every time two vertices merge, you traverse their trees to find the root element, which is the representative element, and if they are not the same, it means that they belong to different trees, and then you can apply a union function which merges the trees. Now, within the unified data structure, there are two rules for minimizing the heights of the trees, because of course the complexity of this algorithm is dominated by the traversal of these parent pointers. And the first of which is called path compression, in which every time you move to a parent vertex in a tree, you point it to the eventual root. And the second rule is weighted union, which is basically always making the smaller tree a child of the bigger tree. Now, with the combination of these rules, the unified data structure has a complexity of O and alpha n, in which alpha is the inverse of Ackermann's function, which for all physical purposes is below 4. So basically, the complexity of the unified data structure is linear. Now, there's one additional aspect of the unified decoder. So remember, we are growing these odd parity clusters in size until they merge with another, until they are of even parity. The extra feature within the unified decoder is called weighted growth. Now, imagine you having an odd parity cluster. Per round of growth, you're adding on the boundary a layer of extra vertices or edges, out of which only one will merge with another cluster. So per round of growth, if k edges are added, only one of these k edges is in the matching. So you're actually adding a lot of faulty edges, which will not eventually be in the matching. So a good way of doing things would be to order the growth of cluster by the sizes, because if you have a smaller cluster, you would add a smaller amount of faulty edges. And again, we have a visualization to demonstrate this. If you have unweighted growth, you have clusters of size 1 and clusters of size 3, and they would grow at the same time. And then you can start peeling. But if you would have weighted growth, it's quite similar. But then you would first grow the size 1 cluster and then grow the size 3 cluster. It happened quite fast, but I think you get the gist of it. So in both cases, the eventual matching is the same, but you can imagine that in some cases it does matter. So to test the union find decoder, we again simulate with similar conditions as before, Pauli noise and Pauli measurement errors with the same lattice sizes, and we get these threshold values. Now they are slightly above the reported ones in the original publication. So we have for unweighted growth weighted growth 9.9, which was reported, and we have 10%. And for the 3D case, which is the Pauli noise and measurement errors, it was reported to be 2.6, but we have 2.7. Now to sum up the comparison, we have the minimum weight matching decoder, which has a relatively high error threshold, but also a high complexity. And we have the union find decoder, which has a lower code threshold, but also a very low complexity. Remember that the alpha is smaller than 4, so it's basically linear. And from our tests, the running time goes up very dramatically, very fast, whereas for the union find decoder, it's quite linear. And if you compare the threshold plots over here, you can see that the minimum weight perfect matching decoder has much better performance. It sits on a different scale. It's shifted by 0.3%. Now, because of the difference in the threshold that we got from our own simulations compared with the threshold that has been reported, we started investigating for the reason behind it. And a result that we've gotten out of it is called, can be summed up in something that is called the matching Way heuristic, which will give intuition and motivation for our eventual contribution, the union find balance boom decoder. Now recall that the reported threshold for the union find decoder for simulations on a toric code on a 2D lattice, which means that it's only Pauli noise. For the non-weighted case, it is 9.2%, and for the weighted case, it's 9.9%. And recall that weighing these clusters means, or weighted growth means that you grow first the smaller size clusters, because they add a smaller amount of edges that will not be a part of the matching eventually. For our own simulations, if we switch off weighted growth, so non-weighted growth, we are getting 9.8% compared to 9.2%, which was reported, and for the weighted case, we're getting 10% compared to 9.9%. So there's a very big difference in the non-weighted case. And we started investigating the differences in our implementation and the original pseudocode that was supplied. And we found out that a major difference is that actually we're maintaining something that we call dynamic forest during growth. So let me visualize this. In the original pseudocode, what it did was to first grow these erasures until they're of even parity, and then make these forests, which are these acyclic graphs. So when growing them, we don't care about whether they're acyclic or not. We just grow them until they meet with another odd parity cluster. And at this point, you make a forest out of this erasure, and then you start feeding them. Now the forest can be made very easily by just picking a random vertex from this erasure, from this even parity erasure, and starting a depth first search or breadth first search from that vertex, and you will end up with a forest by applying some simple rules. However, what we're doing is that in each round of growth, these forests are dynamically maintained, which is why they're called dynamic forests. So each round, we remove the edges that make these cycles within the graph. Now the major difference, so why does this matter? The reason behind why it matter is that if we're growing these forests this way, the eventual forest is equivalent to 2 parallel breadth first searches from these syndrome nodes in the eventual erasure. By doing so, we accidentally made sure that the distance or the weight of the edges between these syndromes are kept at the minimum. So imagine that if you pick a random node here and you started a depth first search or breadth first search, the distance between the eventual matching between these two nodes will be random. But if you do two parallel breadth first searches, the distance between these two syndrome nodes in their matching will be kept at the minimum. So we have now several variants. So we made variants without these dynamic forests. So we have this static forest, which is something that was in the original implementation, and our dynamic forest implementation. We have the non-weighted and the weighted one, and these all have different threshold values. So let me just simplify this in a nice table, which is a little bit easier. So remember that the static forest is the original implementation, and let's call the non-weighted variant the unified non-weighted non-dynamic forest. We don't call it vanilla unified because this is probably still different from the original implementation. We have the unified weighted without dynamic forest. We have the unified without weighted growth with dynamic forest, and we have unified weighted with dynamic forest. So it's quite a bit of a mouthful with a lot of letters and a lot of abbreviations. It doesn't give any intuition of what's happening here. It didn't for us neither. But then we started looking at the weights of the matching of these four variants of the unified decoder. So what is the matching weight? For a given lattice, or for a given erasure, and you start peeling them, eventually what you would end up with is a combination of strings between these syndromes, which are the correction that you apply. If you count the number of edges that are in the correction, that is our, or in the matching between these syndromes, that is our matching weight. And what you see here is that for each, on the left, we have these the threshold values for these different implementations of the unifying decoder, together with the minimum weight perfect matching decoder, and we rank them by their threshold, order them by their threshold. But you can see that if we plot the matching weight, so the total length of edges in the matching, we can see that the order is exactly the same. So if you have a low threshold, it means that you have a high matching weight. If you have a higher threshold, it means that you have a lower matching weight. Now, to better visualization would be to normalize it against the minimum perfect matching, which is the smallest weight. So we have the minimum perfect matching line over here, and we subtract that number from each of these lines of the unified variance, and we end up with is something like this. And you can see that the order is very apparent here. We have blue, yellow, green, and red, and that is exactly the order that we have here. So based on this, we can say that it gives us an intuition that a lower matching weight is an heuristic for an increased threshold. So because of this, we can think, and because of this, maybe we can start even further reducing the matching weight in the context of the unifying decoder to further increase its threshold. So looking back at our comparison, we have this the minimum weight perfect matching decoder, which has the minimum weight and it has a high threshold. What if we can compare this? What if we can combine these two decoders in the sense that we alter the unifying decoder to have even lower weights, such that we can end up with a decoder that has a low complexity and a high threshold because we lower the weights of the matchings. This is what we do in the unified balanced Bloom decoder. In this chapter, we'll be introducing a new parameter called the potential matching weight. We'll be utilizing a new data structure called the node tree data structure. we'll cover the calculations that we'll perform on this new data structure, and again we'll go through the performance of the decoder, especially combined with the unifying decoder and the minimum weight perfect matching decoder. So the potential matching weight is a local variable specific to a vertex in an odd cluster, and it's defined as, let me call myself, the potential matching weight of a vertex is the weight of a matching if a union with another odd cluster occurs on an edge supported by that vertex. So it's a let's look at an example. So this is a very small cluster of size 3. It has 3 syndrome vertices, as I call them, as each of these vertices is a syndrome. So it's a non-trivial parity measurement. If we look at the matching weights, if an odd cluster is merged with this cluster on either one of these edges, we'll see that it's different per vertex. So if a merge with another odd cluster occurs on the first syndrome vertex, the eventual matching weight will be contained within this subcluster, and the new added edge will be 2. If merge with another odd cluster occurs on the third vertex, syndrome vertex, the matching weight will be also true. But if the merge with another odd cluster occurs on the middle vertex, then the eventual matching weight will be 3. So the potential matching weight is a prediction, actually. So based on the structure of the current odd cluster, we can give a prediction or a potential to each of the vertices in the cluster on what the weight of the matching will be if a merge happens with another cluster on an edge connected to that vertex. And that is why we call it a local variable, because it is you only look at the cluster itself. You don't look at all the other clusters on the lattice, even if it's very close or if it's very far. You only look at the cluster itself. In minimum weight perfect matching, that is something that you do. In minimum weight perfect matching, you look at all the vertices on the or the syndromes on the lattice, and you're trying to make this fully connected graph, and you're trying to find the minimum weight subset within that graph. Whereas here, you only look at each cluster individually. And I like to stress that the potential matching weight is only defined for odd clusters. Of course, if there is a fourth vertex connected right here, then the potential matching weight, it's not defined. You cannot say what would be the weight be if another odd cluster is added, because the cluster is already even, and it's specific for each vertex within the cluster. So let's look at an example of a larger odd cluster where I've labeled the potential matching weight of each vertex individually. So we have 7s, we have 8s, and 9s and 10s. If we would grow this cluster according to the vanilla unifying decoder, edges will be added to the cluster across the entire boundary within the same growth iteration. And based on this potential, that will be unfair, because that will be unfair. If you would like to achieve a minimal weight within while growing these clusters, what you would prefer to do is to grow the vertices with the low potential matching weight first, and then move on to the higher potential matching weight clusters. So let's just visualize this. If you would grow this according to the vanilla unifying, and note that we have these dynamic forests as well here, then all edges will be added to the boundary simultaneously per growth iteration. Now, there is actually something that we can utilize to minimize these potential matching weight calculations, because if you would have to calculate these potential matching weight for every vertex in your cluster, then the complexity would grow eventually. And luckily, with our data structure, which is the node tree data structure, that isn't necessary. So let's again consider this with an example. We again have this size 3 cluster of 3 syndromes. and we label them by 1, 2, and 3. As we showed before, they have different potential matching weights of 2, 3, and 2. In the union find data structure, which I call the vertex tree, which is, by the way, still necessary. So the node tree data structure and the union find vertex tree, they coexist. This is how the node tree, the vertex tree would look like. If we grow this cluster by growing the lower potential matching weight vertices first, so the outer vertices here, this is what the vertex will look like, the cluster will look like. So we would add extra vertices on the boundaries of the first and the second, or the first and the third vertex. And within the union find data structure, the vertex tree, all these newly added vertices will be pointed to the root, which is the vertex 0 here, and that's how it's done within the vertex tree. Now recall that the potential matching weight of a vertex is defined as the weight of a matching if in union with another odd cluster occurs on an edge supported by that vertex. So the most important here is that it's the weight of the matching that's important here. So imagine if 0, 1, 2 are syndrome vertices, but the newly added vertices 3 through 8, they are not syndrome vertices. So they are just normal vertices. They're not equivalent to a non-trivial parity measurement. Then if we grow it another round, if a matching occurs or a union occurs on vertex 3, 4, or 5, the eventual matching that occurs will still be with syndrome vertex 0. And the same is on the other side of the cluster. So if a union with another odd cluster occurs on vertices 6, 7, 8, the eventual matching will still be with 2. And these nodes does have the same of these vertices. I got a little bit ahead of myself. These vertices have the same potential matching weights. So we can combine them into a reduced graph, basically, in which the vertices which are grown with the same root syndrome vertex, they belong to the same so-called node. So this, so if we go back to our previous slide, basically, when we have the size 3 cluster here with this vertex tree, the node tree will be initially of 0, 1, 2, because all of these vertices are syndrome vertices. But as they grow and we add a layer of non-syndrome vertices to the cluster, the unified vertex tree increases in size. However, the node tree stays the same, because these new added vertices, they belong to the same node. And that is why it is called the node tree. So it's not, the elements of the tree are not exactly vertices. They incorporate a larger amount of vertices in each node. So let's make the comparison between these data structures. And I would like to stress that it doesn't replace the unified vertex tree. It must coexist, because the function of the unified vertex tree is cluster identification. And that is something that we still need, because we're still growing these clusters and they're still merging and growing. The function of the node tree is to store these potential matching weights for each node and all the vertices belonging to that node. This tree in the tree structure of the vertex tree, the edges, or pointers, actually, they are parent pointers. They exist for cluster identification. Whereas in the node tree, the edges of the tree, they are kind of they might be one edge, or they might be multiple edges in the graph representation. So the node tree basically is a reduced graph, or reduced tree of the reduced forest, actually, of the graph representation of a cluster. The node tree is a reduced forest of the graph representation of a cluster. Does the tree deform within the unified vertex tree, it does due to path compression. Remember that we like to point all parent vertices within the vertex tree to the same root in order to reduce the height of the tree, which is why we have a almost linear complexity for the unified algorithm. Whereas in the node tree, the tree does not deform. And in the tree merge, when tree merges within the unified vertex tree, we can apply weighted union again to reduce the complexity. Whereas in the node tree, we just apply a union. There are some specific rules involved, which we will see later. So given the definition of a node, which is a set of vertices with the same potential matching weight, we define here the bloom of a node, which is growing all the boundaries of all vertices belonging to that node. So the growth of a cluster is now equivalent to the separate blooms of all the nodes within the node set of that cluster. And to delay a node means to suspend the bloom of a node for a number of iterations until an equilibrium is reached within the cluster. And this is the idea of balanced bloom. What we do here is we grow first the nodes with low potential matching weight, and we delay the growth of nodes with a high potential matching weight until there is an equilibrium of potential matching weight within the cluster. So this idea is kind of reminiscent of weighted growth in the normal union-find decoder, except that now we're also weighing parts of the clusters as well. Recall that weighted growth is to grow the smaller size clusters first, and now with balanced bloom, we're growing the nodes with the smallest potential matching weights first. And what's nice about these node delays is that we can actually calculate this delay by just a depth first search of the node tree, where the delay value of each node is only dependent on the node itself and the delay value of its parent. So utilizing this, we can make a decoder that is called the union-find balanced bloom decoder. And if we look at the example cluster that we used before, in which we have these 7, 8, 9, 10s as potential matching weights, growth within the unified balanced bloom decoder now means to first grow the 7s first, then the 7 and 8s, then the 7, 8, 9s, and then the 10s in the last iteration. Now, of course, in this example, it doesn't really matter because this is just to showcase the growth, but you can imagine that in some cases, we can achieve a lower weight by doing so. Now, as I said before, there are some specific rules involved when we try to merge these node trees, and that's what we will cover here. So after a union of clusters, the node tree structure changes, and because of the change of structure, we have to recalculate the delays. And before we do that, we can classify these unions in 3 categories. The first one is odd-odd, a union of odd and an odd cluster. Odd and odd equals to even, and in an even cluster, we cannot define potential matching weight, so we don't calculate the delays. The same is true for even merges. However, if we have an odd to even merge of clusters, of union of clusters, what we end up with is a new odd cluster. And this is when we have to recalculate some of the delays. Now, as I'm saying that, as I said before, the delays in an even cluster is undefined. So what we do to reduce the recalculation of delays is to preserve the calculated delays in the odd cluster in the merge by pointing the merging node of the even cluster to the odd cluster. So as an example, we have this merge of 2 node trees. We have the first node tree N1, N2, and N3, and we have the second node tree N4, N5. And the union happens between vertices of N3 and N5. Because N4, N5 is even, we point N5 to N3, which means flipping it around basically in this representation. And then in order to recalculate delays, we only have to do a partial delay depth of search from node 3 to node 5 to node 4. Why is this? Because recall that the calculation of these delays is dependent on a depth of search of the node tree. So it's very much dependent on the direction in which the node tree is traversed. By doing so, we preserve the depth first search direction in the even part, and we only have to redo the delay calculation in the. We preserve the calculation in the odd part, and we only have to redo the calculations in the even part. And by using this rule, what we end up with is a worst case complexity of O n log n for the entire decoder. Now let's just investigate the performance of the unified balanced Bloom decoder for small lattice sizes. So when we simulate on a toric lattice for independent powder noise for lattice sizes 8 to 48, what we get is that the unified decoder performs very well with the threshold value of 10.25. Recall that the threshold that we got for the vanilla unified decoder, which might not be vanilla at all, is 10%. Whereas for the in the 3D case, so for party and measurement errors, we're getting 2.85, which is quite high because we got 2.7 for the normal vanilla unifying decoder. And what's even more striking is that if we plot the matching rate heuristic, so we count the number of edges in the matching as a comparison between the unified weighted dynamic force, so that is the best implementation that we got, that is the implementation that got 10% threshold, with the new UF balanced Bloom, with minimum weight perfect matching, we see that the UF balanced Bloom, unified balanced Bloom, sits in the middle and very near minimum weight perfect matching. So if we compare this with the variance of the unified decoder that we had before, which was without weighted growth, without dynamic forest, with weighted growth, without dynamic forest, and so on, where the red one is the best one we got with 10% threshold value, with weighted growth and with dynamic forest. The unified balanced Bloom decoder sits right there. It's very, very near minimum weight perfect matching in terms of weight. And I would like to stress that the intuition that a lower matching weight is heuristic for increased threshold, it seems that it is right. So if we go back to our comparison of these decoders, we have the minimum weight perfect matching decoder with a high error threshold but a high complexity. We have the unified decoder with a relatively low threshold but a very low complexity as well. And we have the unified balanced Bloom decoder, which has a complexity that is still quasi-linear. And if you compare it with the graphs that we have before, we can see that the threshold is very near minimum weight perfect matching, and the running time as well is performs really well. It's slightly above, even though it's quasi-linear and not almost linear. It sits just slightly above unified, and it's drastically better than minimum weight perfect matching. However, if we investigate for bigger lattice sizes, it seems that the improvement of unified balanced Bloom over unified is less prominent. So for larger lattice sizes of 40 to 80 for toric code, the error threshold of the unified balanced Bloom goes back to 10.10. So it's still improvement. It's still better than 10.10, but it's less than 10.25 what we got. And in terms of the 3D case, it goes back to 2.78. So it's still a 0.1% improvement, but it's less than the 0.15% improvement that we got earlier. So in terms of conclusions, we can say that the performance of the unified balanced Bloom decoder is better than a vanilla unified decoder for all lattice sizes. and comparable to mean-weight perfect matching for small and medium lattice size with quasi-linear complexity. So as a conclusion, we can say that the performance of the unified balanced room decoder is better than a vanilla unified decoder for all lattice sizes, and comparable to medium-weight perfect matching for small and medium lattice sizes with quasi-linear complexity. And there is something else to conclude, that the lower weight matching weight is a heuristic for increased threshold. So I think that there's still improvements to be made to the unified decoder and as well as the unified balanced bloom, with the goal of minimizing the weight of the matchings. The code that I've used for the simulations, as well as a lot of the visualizations, the animations that I've made are made by myself. It's a code package for simulation of service code, and it can be found at the following link. I would like you to encourage you to visit it, look at it, and contribute to it if you would like. And I would like to thank you for listening, and yeah, that's it.